So this is exponential growth and decay. So up at the top, you have two formulas. Notice they don't look any different, okay? So growth and decay problems, which typically in here we do half-life, but half-life is a decay. Things are going down. Notice the formulas are the same. Everything is the same. The only difference between growth and decay is that the constant that you use, the growth constant, for growth will be a positive number, and for decay, or the half-life, it'll be negative, okay? And for every one of these problems, remember, when you're writing an equation, always for exponential growth and decay, your function, you have to know p sub 0, which is your initial value, and you have to know the growth constant k. Those are the two have-to-knows before you can solve anything else of the problem. So that's what we're going to do today, is solve these problems, look at those. It involves logarithms, so that's why we're doing these now. All right, so 1 and 2, Dr. Taylor did. So let's look at number 3. So this is a growth problem. All right, so a bacteria culture initially contains 600 cells and grows at a rate proportional to its size. So it doesn't give you the growth rate, it just says it's proportional to its size. So we're going to have to find that in a minute. After 5 hours, the population has increased to 620. And the first part says find an expression for the number of bacteria after t hours. So finding the expression means, again, substitute in your p sub 0 and substitute in k. Okay? So those are the two things you have to know. So I'm going to write, you need to know p sub 0, which is the initial amount, which they gave you, 600, and k. And they did not give you the growth rate. It just told you the growth rate was proportional to its size. So we need to find k. Once we find k, we can write our formula. All right, so starting with the formula, just going to write it down. And a lot of you guys learn this as PERT. Remember P, E to the RT? It's exactly what that is. So k is just another way to say R, the rate. They just call it a constant. They use a k instead of c. So if you don't want to use p sub 0, that's just p, the initial amount, and then k is the same thing as r. So all these formulas really just go back to that PERT formula you learned way back when. That's all it is. All right, so let's substitute in what we know. So we know p sub 0, the initial amount is 600. Okay, we don't know k, that's what we're going to look for. And the time, okay, it says after 5 hours, we went up to 620, the population. So t is going to be 5, and then p of t over here on the left, that's your new amount. So after 5 hours, we were going to end up at 620. So if you have a problem where you know every single number except for one, you can solve for that missing variable. Okay. So all of these, so I say I get kind of bored after doing these a few times. All of these, you solve them the same way. First step is to divide p sub 0, get it out of the way. So we're going to divide 620 by 600. Then you're going to write it as a natural log, and then you're going to solve. So they're always the same steps. So that's why most of you don't have any problems with these. All right, so we're going to divide 620 by 600. And you can leave it as a fraction. You can do a decimal. Just remember, if it's a decimal that does not terminate, like this one, when you do your calculations for WebWorks, don't round it. I will round it on paper, but don't round it to do your computations, okay? All right, so 620 divided by 600, we'll call it 1.03. I'll just put a bar over the 3. So it's repeating. And then we're ending up with e to the 5k on this side. All right, so then you're going to write this as a natural log. Okay, so always the natural log of the answer, so it's going to be the natural log of 1.033333 equals the exponent. So the natural log of that number on the left will always equal the exponent. That's how you convert it. And then you're just going to divide the natural log of 1.033 by 5. Okay, so you'll get your value for k. It's the natural log. And don't round that when you put that in your calculator. All right, so I'm going to do natural log. Oops, didn't mean to do that. Natural log of that then divide that by 5. All right, so there's your growth constant. Again, don't round that when you're working with it, but I will round it. I guess I'll go out to, I'll make that 558, and I'll stop there when I write it. All right, so our growth constant is 0.006558. So I'm not done with my problem yet. It said find the expression, so now I can write my expression. So we'll say P of t equals the initial amount, 600, okay, e to the 0.006558 t. That's your expression. Okay, so that's a formula. So when you do exponential problems, the formula must contain the initial amount and the k value. Okay, t is going to just be the variable t. So now that you have this formula, it doesn't look like a t. So now that you have this formula, you can solve the rest of the problem. All right, so part B, find the number of bacteria after 7 hours. So now all you got to do is put 7 in for t. So that's just straight work it out in your calculator. So we want to find P of 7. So that would be 600 e to the 0.006558 times 7. I wrote some of these down so I wouldn't have to put all this in the calculator over and over again. So I got 600, just make sure you're getting these right, 0.185. And those are how many bacteria. Okay? All right. So 628 bacteria would be there after 7 hours. Okay? All right, part C is the only new part. Find the rate of growth, which is a derivative. Okay, find the rate of growth. All right, so let's think about the derivative of an exponential function. Okay, so here's your function. How would you find the derivative of that? Because that's what a rate of growth is for part C. So I'm going to do P prime of t. So we're looking at the derivative of this. All right, so 600 is a constant, right? Stays out front, so leave the 600 there. All right, now what's the derivative of e to the anything? E to the anything. So the derivative would be e to the 0.006558t times the derivative of the exponent. So what's the derivative of the exponent? Just that rate, right? The 0.006558 without the t. So times that. I'm going to put a 0 in front of it. I got too many dots on my paper. All right. So there's the derivative. It's the function, and then just times the derivative of the exponent. So if I want to find the rate of growth after 7 hours, I'm not going to redo all this. What is 600 e to the 0.000 whatever times 7? We already did that, right? That's right there. So this piece right here, we already did. That was what we did right above it. So all you got to do is take 628 times that rate again, and that'll give you your answer. So we're finding the derivative at 7. So I'll put a 7 in there. But we already had that number, so just take that 628 number times that decimal, and you should end up with 4.1196. So this is a rate. So that's the number of bacteria per, we're doing hours, yes. Okay, so the rate that this bacteria, this culture is growing, it's growing a little bit more than 4 bacteria per hour. Okay, last question. When will the population reach 4,000? So when means you're looking for the time. So 4,000 will be your piece of t number. So again, so once you have your formula, you can solve any question they ask you. So now you're going to substitute in 4,000 for p of t, and you're going to solve for t, right? When is that going to happen? So we're going to do 4,000 equals 600 e to the 0.006558 t. Can't make t's today. All right. All right, so now we're back to the same thing. Those 3 steps. Divide by 600, write it as a natural log, solve for t. Okay, last time we solved for k, but it doesn't matter. Whether you're solving for k or t, you're going to do the same 3 steps. So the first thing you're going to do is divide 600 into 4,000. Leave it as a fraction. You can leave it 4,000 divided by 600 and do all your work later. Okay, so it doesn't really matter how you write it. So 6.67 we'll call it, to e to that power. And then we're going to write this as a natural log. So always the natural log of the answer equals the exponent. And then you're just going to divide that natural log by that decimal. And you should end up with approximately 289 hours, a little bit more than that. So that's how long it's going to take for this bacterial culture to grow, up to 4,000. So you guys remember doing these? I'm sure you do. Usually it's not a problem, you just have to set it up. Nice thing about it is you always use that same formula. Numbers always go in the same place, and pretty much you're solving the same way. So once you get your brain around it. So again, the only new thing that we're doing in this section is right there, part C. Find the rate of growth. That's the derivative. Everything else on this section, even in WebWorks, will be just review problems for you. Okay? Good? All right. So now we're going to do a half-life. Same problem, just about, except we're going to be decaying, so our K value should be negative. And then we're going to do a cooling problem. And then we'll move on to section 3.5. So we don't have a whole lot to do in here. These are just for you to kind of have something as a guide for your homework. All right. Half-life of this element is 30 years. And I always say that whatever the element is, it's always got a number attached to it. This is, I guess, cesium. I don't know how to pronounce that. Cesium 137. Some of you guys are going to think, oh, every number in here I have to use. But the number that's attached to the element that has no bearing on your problem. So this is just an element, okay? So that 137 we're not going to use in our numbers. It has nothing to do with it. It's just the name of the element. All right, so we do know that the half-life of this element is 30 years. And we're going to start with a 900 milligram sample. So that's our P sub 0, 900. So part A again, find the mass that remains after T years. So that means write the formula. Leave T in the formula. So we need P sub 0 and we need K. So we have the P sub 0, 900, but we don't have K. So we're going to do exactly like we did on the last problem. So here's our formula. I'll write it down to the KT. And we're going to substitute in what we know. So we should know everything except for K. So P sub 0 is 900. The half-life is 30 years. So that's the time, 30 years. So what would P of T be after 30 years?
450.
450, right? That's the half-life. So 900 milligrams after 30 years will be 450. So they don't give you 450, but they tell you it's a half-life, so half of 900 is 450. So now we're going to solve this just like we did. Same steps. So divide by 900. So 450 divided by 900 is 0.5. E to the 30K. Write that as a logarithm. So the natural log of 0.5 or 1/2 equals 30K. So do the natural log of 0.5 divided by 30. And you should get a negative value since it's going down. Negative point, call it 0.23. I know it goes on farther than that, but again, on paper you can round. Just don't round when you're doing your work. All right, so our formula, P of T equals 900 e to the negative 0.023 t. So once you have that, you're good to go. The rest of the problem, you're just plugging in numbers wherever they need to go. Okay, so that's kind of the hardest part of the problem is finding your formula. All right, so part B, how much of the sample remains after 150 years? So where's 150 going? And for t, right? So you're just going to put 150 in there, and that's just straight out calculator. So p of 150, 900 e to the negative 50. So no logs needed in that one. 28.13-ish. And again, I didn't round on these answers, so if you put in what I have here, it might be a little bit off. So remember, when you're getting your answers, especially for WebWorks, I'm not so picky on it. If I see your steps and you round it, I'm good. But WebWorks doesn't like that so much. So just make sure you keep that whole expo or the whole k value in your answer. All right, and part C. After how long will only 4 milligrams remain? So where are you going to put the 4 in here? How long will only 4 remain? So 4 is going to go here, right? That's the new amount. So 900 is going to go down to 4. So you're going to solve for t. How long does that take? So for part C, this one does involve logs, but same way you do it. Okay. So divide 4 by 900, and then write it as natural log. So. All right, so that's 0.004 repeater. Right. All right, so take the natural log of that and divide it by 0.023. All right, so that one you should get 234-ish years. That's how long it's going to take to go down to 4. Okay? All right. All right, so that was a growth, a half-life, and I am not going to do the interest problems with you because those are the very basic ones you probably started in Algebra 1 with. So Dr. Taylor did those two with you. So if you didn't do them, you can do them. The formulas are there for compound interest and for, this is compounding interest formula when your money is compounded so many times a year. So monthly, daily, okay? And then you have your compound interest for continuous, when it's growing continuously. So for number 5, it says how much money do you have if your money is compounded monthly? So that's this problem. And you would use 12 for n, since there's 12 months in a year. And then number 6 says how much do you have if your money is compounded continuously? So continuously you use PERT. Anytime you see the word continuous, it's PERT formula. Otherwise you use that one. Okay, so I'm not going to do those with you. Those are just substitute in your numbers and plug them in your calculator. You don't need any logarithms. You don't need anything. So those are pretty basic. Okay, so just remember those formulas. You do need to know the formulas. I don't give you those. Okay. Remember, the only formulas I'm going to give you on this test are the volume or surface area ones for the related rates. Those are the formulas you would be given. Okay. All right. So let's look at the very last one, that Newton's law of cooling. Okay. All right. So I don't want you to panic with these formulas because they really are the same thing as what we've been doing, but I want to go through that with you. So I use this formula because it looks pretty much like what we were doing. This one looks a little more scary, but they're really the same. Okay. So Newton's law of cooling, we're going to do temperature of taking a turkey out of an oven, which isn't very exciting. I need to change. I keep saying I'm going to change this form. I never do. To me, Newton's law of cooling is more fun to do. This is the formula that they use, you know, when you watch all those crime shows on TV when they're figuring out time of death. Because they can take the temperature of a body and, you know, if they're outside, what's the temperature outside? They can figure out how long, you know, how long ago was the temperature of the person, 98 degrees, so they can figure out when that person died. This is what they use. So we're going to do a roasted turkey. It's not as exciting, but same thing. He's already dead. He's in the oven, so we're going to do the same thing. But this is that kind of formula. So if you look at the left side, I don't like this one, but we'll use it because it's really C. So this T sub 0 minus T sub S is the same thing as C. If you notice, everything else in the problem is the same, right? So you have e to the kt, which we've been doing. And then you have a new thing added to the end, which is T sub S. So T sub S is the surrounding temperature, because it matters. So if something is cooling off, let's say a cup of coffee you get from Starbucks or wherever, and you're walking outside where it's 30 degrees, your coffee is going to cool off a lot faster versus if you're in the building and it's only 70 degrees in the building or whatever. So T sub S is the surrounding temperature. Okay, so C, which we were doing the initial amount, right? That was the P sub 0. So think about C, your initial amount. So if I go down here and look at what C is, it's the initial temperature minus the surrounding temperature. Okay, so we have to subtract the surrounding temperature from the initial temperature. That's going to be your starting point. So over here, it just tells you T sub 0 is the initial temperature and T sub S is the surrounding temperature. So this is C. Okay, so it's just showing you how to find C. Okay, everything else is the same. We solve them the same way. All right, so in this problem, we have a roast turkey. We're taking it out of an oven where the temperature, when its temperature, so when the turkey's temperature reaches 175 degrees Fahrenheit. And then it's placed on a table in a room where the temperature is 65 degrees. All right, so T sub S, the surrounding temperature, is 65. Okay, that's the surrounding temperature of the room. All right, what is C? What are we going to put in our formula? That's the initial temperature minus the surrounding temperature.
175 minus 65.
So 175 was the temperature of the turkey, but the room is 65 degrees. So C is going to be 110. Okay, it's the only difference. Everything else is pretty much the same. Okay. All right, so this time when we write our formula, we have to know the initial amount C, which we just found. We have to know K, which I don't know yet, and we know T sub S. So that's the new piece, is that you have to add that 65 degrees onto the end of the problem. So we have to find K. Okay? So look at part A. It says if the temperature of the turkey is 155 degrees after a half an hour, what is the temperature after 45 minutes? So I got to do two parts here. Before I can find the temperature after 45 minutes, I need to find K. I always have to know K before I can plug in a time. So I have a little problem because one says half an hour and the other says 45 minutes. So I have to use the same units. Okay? So if you're going to use 1/2 and you're going to keep this in hours, then you would use 3/4 for 45 minutes. My guess is most of you don't want to use fractions, so I'm going to change it to minutes. So how many minutes is half an hour? 30. So I'm going to use 30 for half an hour. That way everything's in minutes. But if you wanted to do it using the hours, that's fine. Okay, you just change both to hours. Okay. All right, so let's look at our formula. So we have T of T equals, I'm just going to write it, and we'll plug in stuff. Okay, so I got to solve for K, which means I should know everything else. All right, so we'll look at part A again. The temperature is 155 degrees after 30 minutes. Okay, so let's start with that. So we're going to start with our C value. That was 110. Remember, we found C. E K to the 30. So 30 minutes goes with what temperature, which is what's over here on the left. So that would be the 155. So the temperature after 30 minutes was 155. And then we have to tack on the surrounding temperature to the end of this formula, plus 65. So without that 165, it's really the same thing, right? The initial, the time, the new amount to solve for K. But we just have to add on that 65 to the end. So when you solve this one, you have one new step, subtract 65 first. Okay? And then everything else goes the same. So the first thing to solve for K, we're going to subtract 65 from both sides. So 155 minus 65 is 90. And now it looks pretty much like it did. So now we're going to divide both sides by 110, write it as a natural log, and find your value for K. Okay? So divide by 110. So, 0.81 repeater. Okay. And that's e to the 30k. So we're going to do the natural log of 0.818181 and then divide it by 30. So you should get a negative rate because the temperature is going down. 0.06689. Does that sound right? 0.006689. I'll just leave it at that. Okay. So I haven't answered the question yet. The question is, what is the temperature after 45 minutes? Now that I know my formula, then I can just plug 45 into it. So your formula is 110 e to the negative 0.006689 t plus 65. That's your formula. So again, all formulas, you got to know the initial amount and you have to know K. Yes?
I mean, if we use like a half for the hour, it's going to be different, right?
Yes. Yes, but then you're going to plug in 3/4 for your time, right, for 45 minutes. So you'll get your answer. Your answer is going to be in hours. My answer is going to be in minutes. But if I take my answer and divide it by 60, I will get your answer, right? So, and I don't know, WebWorks might ask you how many hours or how many minutes, so we'll talk about that in a second. So yes, if you used half an hour instead of 30, your K value is going to look different. But then right now, we're going to find the temperature after 45 minutes. So I'm going to plug in 45 for T. But if you're doing the hours, you would plug in 3/4 for T. That's 3/4 of an hour. So just keep your units the same. It'll all work out in the end. Okay? So we're going to find the temperature now after 45 minutes. So all you have to do is 110 e to the negative 0.006689 times 45, and then don't forget the plus 65. So I did this in minutes. No, this is the temperature, right? Sorry, you're going to get the same temperature then. I'm sorry, I thought we were doing time. We're doing temperature. So that's what I got. So either way, you will get that, okay? I'm thinking about part B already. So if you used hours, you will use 3/4 instead of 45, and you should get the same temperature. Okay? All right. So we good with that? Yeah, the dead bodies are much more fun, but I keep saying I'm going to change it, and I just never remember. All right, so part B. So now, when will the turkey have cooled to 110 degrees Fahrenheit? When? So you're using this formula right here. Okay, there's our, always we're going to start with that. And you're going to put 110 right here. When will this time equal 110 degrees? Okay, so 110. Looks weird because they're both 110, but we're going to subtract 65, so that's going to change. All right, so you're solving that equation for T. When will the temperature of the turkey be 110? Remember, it started off at 175 when you took it out of the oven. All right, so subtract 65 from both sides. That's 45. Divide by 110. And then do your natural log. I told you, do the same thing. It's kind of... All right, so 45 divided by 110. So 409, 09 seems to be repeating. All right, and then just do your natural log of that. Just the 09 repeats, not the 4. All right, so that's I got 133.625 minutes. Again, if you're doing hours, divide that by 60, you end up with 2.23 hours. So I think WebWorks wants hours, but I can't remember 100% on that one. So you can still do it in minutes. It doesn't change the fact. It's just, it'll tell you what to write the answer. Okay? All right, Sean, so we can stop on section 3.4 here.